Okay, let's start reviewing some important concepts related to hypothesis tests, and let's begin again with creating a sampling distribution. And specifically, we have a healthy population of female children aged 5 that has a population average of roughly 18 kilograms with a standard deviation of around 2.5. So that's the sigma. So we know the population standard deviation, meaning we can actually work with a z-score. Okay, so now imagine you draw 10,000 random samples from a population and calculate for each sample the sample mean. How does the distribution of the sampling means differ when the sample size is once 2, so very small, and once it is 100? Illustrate by sketching two sampling distributions, one stylizing a sample size of 2 and the other stylizing a sample of 100. So the difference is that the greater is the sample size, the more representative is your sample. So that means there is less variation around the true mean. And the sampling distribution of those means, they look much narrower around a certain mean than, for example, something which is having only a sample size of 2. If you have a sample size of only 2, there is much more probability mass in the tails and much less in the middle, and so the blue line would be roughly the sampling distribution of a higher sample. And that is related obviously to the standard error. So the standard error is the standard deviation of the sampling distribution, and you see if the standard error is equal to the population standard deviation over the square root of n. Well, if n goes up, the sample size goes up, the standard error becomes less. You can actually draw that in Excel too. So I know I want to draw it to distributions with a mean of around 18, and I know that once you are 3-4 standard errors away in each direction, the values become 0. So I think because the standard error for the small sample size is around 2.5 over the square root of 2, so that's around 1.4. So yeah, I think if we go maybe, if you have here 18, so here we will have a mean of 18, and once we have a standard error, once it is 2.5 over the square root of 2, and once it is 2.5 over the square root of 100. So it should be enough if I just draw something which has maybe the lower end is maybe 12, and here it is 24, because then I'm enough standard errors away so that the tails become 0. So yeah, so let's do that. So on the x-axis we have now kilogram, and let's say I start at 12, and now I highlight the entire column and I fill this series. I click on editing, fill series, and I fill it with a step value of, let's say, 0.1, and I want to end at 24. Okay, so then I have the sampling distribution, sampling dot dist dot when n equals 2, and then I have a sampling distribution when n is equal to 100. And we can actually draw that in Excel. And the formula that we need is not norm.sdist, because that is for the standard normal distribution, which has a mean of 0 and a standard deviation of 1. But there's another formula in Excel which we can use in order to illustrate those sampling distribution, and that is just norm.dist. So, and that gives us more flexibility with respect to the mean and the standard deviation. But it will be bell-shaped, so that's the point. Okay, so now we say for the sampling distribution of n equals 2, we know, okay, we want to know how far away is the 12, so we go norm.dist, not sdist, norm.dist, open parentheses. Okay, I want to know what's the probability of getting a 12 when the mean is 18, comma, the standard deviation is, I can actually enter the formula in Excel, 2.5 divided by the square root sqrt over 2. And now you don't want the area to the left of 12. You want basically the y-axis value. So we have to put false or 0. Okay, so now, as predicted, we get a pretty small number. We can copy down that formula. Now we do the same, assuming a sample size of 100, which affects the standard error. So we enter now norm.dist, and I want to know the first value, for example 12. What probability does that have when the mean is 18? And now for the n equals 100 sampling distribution, or 99 degrees of freedom, but the standard deviation is now 2.5 divided by the square root of 100. So it has a much smaller standard error. And again, we don't want it cumulatively 0. Okay, so that's an even smaller number. Let's copy that down. And okay, so now we can just visualize it, and then we get actually the exact sampling distribution. So now let's see what it looks like. So we highlight the entire data array, and then we go to Insert, Recommended Charts, and here it is. We can take, so that would be the two sampling distributions. You see the mean is both 18. Maybe we can make that a little bit nicer on tick marks. And the labels. And yeah, we can also smooth the lines a little bit. So if we right click Format Data Series, you click on that formatting bucket, you can check the smooth line. And the other one looks pretty okay. So, but yeah, so this is how we get our sampling distribution. So we have drawn these here. And what's the mean and the standard deviation? Well, here the mean is 18, the mean is always the same, and here it's 18. But here the standard error is equal to 2.5 divided by the square root of 2. So that would be 1.7 1.768 or 2.5 over the square root of 2, and here the standard error would be 2.5 over 10 or 0.25. Okay, but the point is, a more representative sample reduces the standard error. Okay, so what's the probability of drawing from the population a random sample of 25 that averages out to a sample mean of x equals 17? Okay, since we already have Excel open here, we can quickly create the actual sampling distribution for n equals 25. Okay, so now the norm_dist function simply changes to norm.dist, open parentheses, A2, 18 the mean, and now 2.5 divided by the square root of 25. And we can copy that down. And now let's take a look at this sampling distribution by going to Insert, Recommended Charts. And so now here we see the sampling distribution. Let's put it up here. Okay, let's format it again a little bit nicely. Let's put everything with tick marks. Format axis on tick marks, maybe 10. Labels, specify interval unit 10. Okay, so now in this sampling distribution, maybe we can add the grid lines. Okay, so I want to know what's the probability, if this is my sampling distribution, that I draw a 17 or less. So I gotta move again to this side. So that is, I'm interested in this area here. So in other words, what's the probability that the sample of 25 averages out to a mean of 17 or less? Okay. So that is this area here, the yellow one. So that's pretty straightforward. So what we need to calculate is the critical z, and we can use the z because we know the population standard deviation. So our, actually not the critical t, our test z. So our test z, our z-score is that an average of 17 in the sample of 25 and the mean is 18. Well, that is 17 minus 18 divided by the population standard deviation, 2.5, over the square root of 25, which is 5. So that becomes -1 divided by 0.5 or -2. So I need to find in the z distribution the area to the left of -2. And that is equal to, so now we have to use the norm.s dist. So we do norm because now I want to know the value in the z table, which is the standard norm norm.s.dist. I want the area to the left of -2, and now I want it cumulatively because I don't want the y value, I want the entire area to the left. Okay, so that probability is roughly 0.0228. Okay, so we would write the probability of x less than or equal to 17 when n is 25 and the standard error is 0.5, well, that is 0.0228. Okay, so what's the probability of drawing one single observation from the population with a weight of 17? So I'm not looking at the sampling distribution, I'm actually looking at the distribution as it is, at the population distribution. So that means, you know, the n is actually 1, right? So we can then say that the normal distribution is given by a mean of 18 and a standard error of 2.5. Okay, now we copy down this one. Now we have to find again our graph. Well, and now you see that our 17, actually a good example. So now our 17 in a population where the mean is 18 and the population standard deviation is 18, well, that has obviously a much higher probability, right? So now we are interested in this area here to the left. So how do we calculate that? So now our z-score is simply, I can do that here, so our z-score that we are interested in is now 17 minus 18 over our standard deviation in the population of 2.5. So that is -1 over 2.5. So that is everything to the left of -0.4. Okay, so now what we need to change is in the formula, the -2 to the -0.4. And now we get an area of roughly 34.5%. So the probability of drawing an xi which is less than 17 from a population with mean 18 and a population standard deviation, not a standard error, of 2.5, that is equal to 0.345. Okay, so now that was a review again of the sampling distribution, and yeah, let's stop here and then let's do another problem set again on sensitivity and specificity, but I do that in a separate video. So let's just stop here and let's continue in a separate video next.